When a local resolver does a recursive lookup on behalf of a client, it sends DNS queries to various DNS servers on the internet. Normally, this traffic is UDP, as we have looked at in previous lectures. Since there is no handshake or state in UDP like in TCP, we cannot be sure that the response is coming from the server we queried and that the data is valid. Let's have a look at an ordinary lookup where our client asks the local resolver about the IP address of www.google.com. This information is in our case not cached in the local resolver, so it has to do a recursive lookup to find the answer. In the example, we have skipped the iterative lookups sent to the root servers and the .com TLD DNS servers. Maybe that information was cached already by our local resolver. So the resolver sends a DNS query to the authoritative DNS server for google.com. Let's assume that the IP address of this server is 8.8.8.8. This is an UDP packet with a destination port of 53 destined for 8.8.8.8. The server responds with a DNS answer giving us the IP address of www.google.com, which the local resolver sends back to the client so it can do whatever it wants with it. Maybe HTTP to the Google webpage or whatever. But since the DNS traffic is UDP, what if an evil host on the internet sends the DNS replies to our local resolver, telling it that the IP address for google.com is something different? By doing that, he can trick our client to browse to a fake Google page for further attacks. If the attacker succeeds, he does not only fool our single client, but since the local resolver normally caches information, this forged DNS entry is cached and sent out to any client using our local resolver as long as the data stays in the cache. This spoofing attack can happen in any level of the recursive lookup. Imagine our attacker tricking all clients using the resolver that the authoritative DNS server for TLD.com is 66.66.66.66. After successfully injecting this data in the cache, the local resolver will send DNS queries for any .com second-level domain to 66.66.66.66, which is then able to redirect all clients wherever he wants. So, what are the requirements for this attack? First of all, the attacker must be able to send an IP packet with a spoofed source address. Generally, this is not a problem at all. The countermeasures for IP spoofing are techniques like unicast reverse path forwarding and anti-spoofing access lists. These countermeasures make sure that the attacker host with its real IP of 6666 cannot send out IP packets with other source addresses. Both URPF and anti-spoofing access lists must be applied as close to the source as possible, and very few ISPs does this today. So it's quite easy for most people on the internet today to spoof their source IP. When the resolver sends a query to the name server, it wants an answer. When it gets an answer, it does not listen for answers anymore. It means that our attacker needs to send the spoofed DNS reply in exactly the right moment. It must be sent after the resolver has sent the query to the name server, but before the answer gets back from him. You can compare this with standing in a house inside of a window. You open the window, shout out a question to someone, then you wait for an answer. As soon as you hear the answer, you close the window. But you have no idea who shouted back at you with the answer. And if two answers are shouted back at you, you will only hear the first one, because when the second answer hits your house, you have already closed the window. In DNS, this window is open just a few milliseconds. But imagine how many DNS queries are being sent out for a local resolver serving thousands of clients with DNS services. There's a lot of windows being slammed. Next item that needs to be in place for a successful DNS spoof is a transaction ID. This is sometimes called a TXID, and it's a 16-bit number that is part of all DNS packets. When someone sends a DNS query, it contains a TXID, and when someone responds to this, the response needs to contain the same TXID. The original purpose for TXID was to match multiple queries to the same server with multiple responses coming back. see it as if you open many windows and shout out many questions. For each answer you get back, it contains an identifier so that you know which question each answer belongs to. In early days, the TXID was just a number being incremented for each query. First query had TXID 1, next 2, 3, and so on. But in some occasions, there are ways for an attacker to find out the current TXID for the local resolver, and can thereby guess which is the next TXID and inserting that in the fourth response. Nowadays, all DNS server uses TXID randomization. For each DNS query being sent out by our local resolver, the TXID is randomized, and in order for the attacker to send a proper reply, he has to guess the correct TXID out of 65,000 possible numbers. Another number that needs to be matched is the source port. When the local resolver sends a query to 8.8.8.8, this is a UDP packet with a destination port of 53. But all UDP packets also have a source port, which is normally a random value between 1024 and 65,535. For each query sent out, this value is unique, and the challenge for the attacker is to also guess the source port. There is most likely a firewall in front of the local resolver, but this is worth nothing in this case. The moment the local resolver sends out a query, the firewall in front of it takes a note about the source port and will happily allow a response coming back to that source port as destination. So it seems unlikely that an attacker could be able to be faster than the real DNS server, as well as guessing two different 16-bit numbers. Remember that this is a blind attack. The attacker cannot see the traffic coming out from the local resolver destined for 8.8.8 name server. If he could do that, the attack would be much easier. But in this case, the attacker can only guess when the window is open, and guess both the destination port and TXID. And the key to success in guessing is brute forcing. You can be sure that the attacker does not wait for anything before he starts spoofing attacks. Instead, it sends thousands or millions of packets to the local resolver, hammering it with all possible combinations of TXIDs and ports. He can do this all day just waiting for luck. This example is a bit simplified. There are sophisticated ways for the attacker to trigger DNS requests, and as I said, if the attacker could be in line seeing the DNS queries sent out, he would instantly know both the TXID and the source port. The solution to DNS spoofing is DNSSEC. DNSSEC is not covered in this course, at least not yet, but the idea with DNSSEC is to, with crypto, sign all DNS data. By signing the answer coming back from 8.8.8 name server, the local resolver can be sure that the data is intact and has a valid origin. The signing process is done with asymmetric encryption, and the data in this case is signed with 8.8.8.8's private key, which he validates with its public key. And there is today no known ways for an attacker to sign the response, since it does not hold a copy of the private key. DNSSEC is rather complex, and as I said, it is not covered in this course, but it's good to know that its main purpose is to protect DNS data to be altered or spoofed.